Hello again, my friends. The last load sizing heuristic that we are going to discuss is the part period balancing heuristic. Now, I want you to remember what we have done in the silver meal heuristic and the least unit cost heuristic. In summary, in the silver meal heuristic, we were calculating the average cost per period if our order is to span the demand of the following T periods. And we are making a comparison here. We were observing a decreasing function in the beginning, and at some point it increases. And in the least unit cost heuristic, we are going to do we were doing something similar, in which we were calculating the average cost per unit as opposed to the average cost per period. Again, this function was decreasing as we introduced more periods in our calculation because the fixed ordering cost was shared among a larger amount of demand. But after some point, it was starting to increase, and this was the point where we have stopped. Now, part period balancing is less complex compared to these methods, and it is also it's not using an average cost idea, okay? It's not calculating an average cost. It is actually based on another concept that we have already known from the second module. Now, remember when we were studying the basic economic order quantity model, we have developed the economic order quantity formulation by analyzing the total cost function, and we have said that the order quantity that minimizes the total cost function was called the economic order quantity, okay? While we were calculating this formulation, we were just checking the total cost function. It was a convex function, if you remember, and we were taking the first derivative of it and making it equal to 0 to determine the economic order quantity formulation. And then I have mentioned about something. I have told that this value, this economic order quantity, was also making the ordering cost component of the total cost function equal to the carrying cost component. In other words, at the economic order quantity, the ordering cost, the yearly ordering cost, is equal to the yearly inventory carrying cost, okay? Now, though this is a natural outcome of the economic order quantity formulation, we are just going to take this idea, and instead of calculating the average cost per period or average cost per unit, this time we are going to stop at a period at which the fixed cost component, fixed ordering cost component, is approximately equal or very close to the inventory carrying cost when our order is to span the demand of the following T periods, okay? So again, we are going to have an iterative method. We are going to consider what happens if our order is to span the demand of the following T periods, but we are going to base our decision on the difference between the ordering cost component of our cost to the and the carrying cost component, okay? So this time we are going to evaluate a function delta, and delta T is the absolute difference between the ordering cost component and the carrying cost component if our order is to span the demand of the next T periods, okay? Now, if my order spans the demand of one period only, then I pay a fixed ordering cost, but I do not pay any carrying cost. So K minus 0 is equal to K. Remember, I'm always checking the absolute value, okay? If my order is to span the next two periods demand, then I'm going to pay a fixed ordering cost. And along with that, I'm going to pay an inventory carrying cost for the demand of the second period. And in order to carry that to the next period, I need to pay H dollars per unit. So this is the ordering cost component. This is the carrying cost component. And the difference of these two is delta t or delta 2 if my order is to span the demand of the next two periods. Now, if my order covers these requirements of the first three periods, then I will pay a fixed ordering cost. That is the ordering cost component. And what is my carrying cost component? I am going to carry D2 units of inventory to the next period and D3 units of inventory to the period after. So I need to multiply this with 2h and I need to multiply this with only 1h. Now, again, remember my intention here is not to calculate this total cost. I want to calculate the difference between the ordering cost and the carrying cost. Okay. Now, whenever this absolute difference is minimized, I should say that this is the optimal number of periods that I need to spend, okay? Because I know from the economic order quantity model, at the economic order quantity choice, the ordering cost and the carrying cost is equal to each other. Now, it may not be possible here at any number of periods to make the ordering cost component exactly equal to the carrying cost component, but we can go with the number of periods at which the difference, the absolute difference between the ordering cost and the carrying cost component is minimized, okay? So basically, we are trying to imitate the natural results of the basic economic order quantity model here, okay? And if my order is to span the demand of the next T periods, then what I'm going to do, I'm going to pay a fixed ordering cost of K dollars, and my carrying cost will be calculated as H times the demand of the next period, 2H times the demand of the period after, blah, 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 so on and so forth. And the demand of the T period will be carried for T minus 1 weeks, and for each week I need to pay H dollars per unit. Now, I'm always going to introduce a new period again and again and again. At some point, my friends, obviously, because all added components will always be subtracted from the fixed ordering cost, that absolute value function will start to decrease in the beginning, then it will start to increase after some point. Whenever the addition of the next period is increasing this delta t function, this is the point that I will stop and I say that my order should meet the demand of the next t periods at this point. Then I'm going to start this procedure from the point that I'm going to be left. Now, let's practice this for this problem. My first net requirement is observed in the second week, and at this point, I need to plan an order received, okay? Now, if my order is to span the demand of this week only, then I'm going to pay a fixed ordering cost, but no inventory carrying cost because nothing will be carried to the following period. So the absolute difference between my ordering cost component and carrying cost component will be 0. Now, if my order is to span 2 periods, or 3 periods, or 4 periods, or 5 periods, it doesn't matter. My fixed ordering cost component will always remain as 100, okay? The only thing that will be changing is the carrying cost component. If my order is to span the next period's demand, then I need to pay $40 of inventory carrying cost for this problem. Remember now, each unit carrying cost is $1 for each period. Now, the absolute difference between the ordering cost component and the carrying cost component is 60. As you can see, it is reduced. Now, if my order is to span the demand of the fourth period as well, which is the third period, the costs will not be affected from that. Neither the ordering cost obviously will not be affected at all. And since there is no demand in the fourth week, the carrying cost will not be affected. So the absolute difference will remain as 60. Now, if I introduce the fifth period to my order, In that case, the ordering cost will remain as 100, and I need to pay $30 more for the inventory carrying cost, and that will be a 70. The difference between the ordering and the carrying cost will be 30. Now, if I introduce the sixth period in my order, the demand of the sixth period in my order, then I need to pay 40 times 4 times $1 of inventory carrying cost. Why? Because for each week, the unit carrying cost is $1. I need to carry the inventory to meet the demand of these 40 units. If I receive an order at this point, I need to carry these 40 units for 4 weeks. So 40 times 4 times 1 is 160. So 70 plus 160 is 230. The absolute difference between the ordering cost component and the carrying cost component has become 130. So there is an increase here. So I say 4 is the optimal number of periods that I need to consider whenever I plan, if I'm going to plan an order receipt at this point. So the order receipt that is to be planned in the second week should be 8 units, which means in the 6th week, I have another net requirement. Okay. So if my order here spans the requirement of this period only, then there will be no inventory carrying cost, but only a fixed ordering cost. The difference between these two is 100. If my order is to span the demand of the next period, then I need to pay $30 of inventory carrying cost. The absolute difference between these two components will be 70. If I introduce the 8 periods demand, which is definitely 0, again, the absolute difference between the ordering cost and the carrying cost component will be 70. If I introduce the demand of the 4th period, which is 30 for 4th period or demand, which is 30 units, that 30 units of inventory would be carried for 3 periods. For each period, we pay $1 for each unit. So my carrying cost will be increased from 30 to 120, my friends. Okay, so the absolute difference between these two values is 20. As you can see, from 70 to here, it has decreased, even if the carrying cost component has exceeded the fixed cost here, we observe a decrease, my friends. Okay, but actually, there is this unnecessary calculation that we have done for the 5th week. We obviously know that since the fixed ordering cost will always remain the same, adding another period with a positive demand here, okay, if we have a 0 demand, adding it will keep the absolute difference here same. But if we observe a positive demand here, since we have already exceeded since the inventory carrying cost is already exceeded the ordering cost, there is no need to make any further calculation here. So this is the optimal choice, but we are still doing it just for fun purposes. If I introduce the demand in the 10th week to the order receipt that is planned in the 6th week, for these 55 units of demand will be met by carrying this 55 units for about 4 weeks. That will introduce 55 times 4, $220 more to my carrying cost, and my carrying cost will be $340. The absolute difference between the ordering and carrying cost components will be 240, which is definitely greater than $20 here. And we have already mentioned that this is obvious, right? Because the fixed ordering cost remains the same at all times. So we say that the order receipt that is to be planned in the 6th week must span the demand of the following 4 weeks. So 40 plus 30 plus 0 plus 30, it should be 100 units. Finally, there is another net requirement in the 10th week. There is no need for further calculation because this is the last week and we need to receive another order at this point in the 10th week, my friends, to meet the demand here, which will be exactly 55 units because we do not aim to carry any inventory to the next period. So we have 3 order receipts and 3 order releases, which must be scheduled 1 week earlier. And that will introduce a $300 of ordering cost. And from second week to the 11th week, the total amount of inventory carried from one period to the next is 190. And this must be multiplied with $1 of unit carrying cost per week. And the total cost associated with the schedule is 490. Now, this result is no better than the result that we have achieved in the silver meal heuristic, but it is $5 better than the result that we have achieved in the least unit cost heuristic. So part period balancing is better. For this instance, it was better than the least unit cost heuristic. Now, as I have told you, it is not actually very practical to make a generalization at this point. So we cannot simply say just because silver meal heuristics does a lot better compared to the other heuristics in this problem, guarantees that it will always do better than the other heuristics. But let me tell you that least unit cost and part period balancing can be sometimes as successful as silver meal heuristic and sometimes the periodic order quantity approach here. Economic order quantity is a simple method which requires no calculation. However, for this heuristic to be successful, we rather need to have a stationary demand behavior, which means, I mean, even if it behaves dynamically, the variance between the consecutive periods demands should be not so large, okay? And lot for lot approach is not basically heuristic. It was just helping us to understand the problem that we have here or understand how we should implement such a lot sizing heuristic. But if you have just-in-time philosophy adapted between your supplier and you, then lot for lot heuristic can do better results as well. I mean, because such relationships, the just-in-time philosophy can only be adapted between suppliers and customers who simply omit the possible fixed ordering costs in their relationship. So such philosophy can be adapted if you have a long-term relationship between your supplier and you. Therefore, in such relationships, we usually do not observe large ordering costs, and that means lot for lot approach can also do better under such supplier customer relationships. Okay, now in general, other heuristics outperform lot for lot and economic order quantity heuristics. So we have seen that. So the last four heuristics, they usually outperform the first two heuristics. Okay, and sometimes instead of using a heuristic which is successful in most cases like silver meal heuristic, sometimes it may be a little bit better which requires the least amount of calculation like part period balancing. Okay, and we say that the load sizing heuristics are more preferable than the optimal load sizing techniques in rolling horizon environments. Now, what is a rolling horizon environment? We repeatedly make the load sizing decisions frequently over long horizons. So let's just say we are trying to make a load sizing decision for the following 20 weeks. After 2 weeks, we revisit our load sizing decision again for the following 20 weeks, which means the next load sizing decision that we are going to make is also involving the load sizes that we have already determined for the following 18 weeks. Okay, so this actually, when you are making a load sizing decision for about 10 weeks, that does not mean the next load sizing decision will be made in the end of the 10 weeks. Okay, so every once in a while you repeat this decision. You basically recalculate your load sizes based on the current information that you have. So because of that reason, every time running optimization algorithms is not going to create a big difference. Okay, so in the end, you are going to update your optimal solutions with the new information that you are going to get. So why you should use so much time or effort for that? Now, There is a paper which is published in 1989 in which we can compare for the last four heuristic methods, the load sizing heuristics that we have mentioned. Now, we should say that the computational complexity of the silver meal and the least unit cost heuristics are the largest. Load for load, economic order quantity, and periodic order quantity approaches are not too complex to implement, and part period balancing it resides somewhere between the complex heuristics and the simple heuristics here. Now, the last three heuristics are usually appropriate to use in almost every kind of circumstances, every type of demand profile. Now, economic order quantity and periodic order quantity heuristics are simple to understand, simple to explain, but they are more successful when we observe a stable demand, okay, a stationary demand. And lot for lot approach should be used when the just-in-time policies are adapted. Now, this paper, Baker, has developed 20 different instances, 20 different test problems in his study. I do not know if he is, or I'm mentioning about a he or she. So Baker has developed 20 test problems, and among these 20 test problems, the number of optimal solutions that this periodic order quantity heuristic has achieved was 7. So out of these 20, for 7 of them, the periodic order quantity approach has resulted with the exact solution that you would get from the integer programming model. Okay, so remember, the last week we have covered the optimal load sizing problem. So the optimal load sizing procedures will always yield you the optimal solution. But out of these 20 test problems, in 7 of them, periodic order quantity approach, the heuristic, also has yielded optimal solutions. Now that value increases to 14 and 16 for silver meal and part period balancing heuristics. So this means in this study, it is estimated that the probability of the silver meal heuristic and the part period balancing heuristics to yield an optimal solution, which is exactly the same solution that you are going to get with the integer programming model, is larger. Okay, the probability of the least unit cost and the periodic order quantity heuristics to yield the optimal solution is less. Okay, but these are just estimations from this study. Okay, again, we cannot simply generalize this study for any kind of demand profile, but I mean, these should give us an idea about the success of silver meal and part period balancing heuristics. But here's the thing. For the silver meal heuristic, the mean percentage error from the optimal solution and the solutions that we get from the silver meal heuristic was very small. Unfortunately, even if out of 20, in 16 of the problems, the part period balancing has yielded the optimal solution, for the other 4 problems, the percentage error from the optimum cost was a little bit larger. So, which means part period balancing, according to these estimates, is doing better to achieve the optimal solution. But if it does not achieve the optimal solution, the deviation from the optimal objective function is a little bit larger. Okay, so this means practically, if you want to have the optimal solution, then part period balancing has a higher probability to achieve that. But if it cannot achieve, then the deviation would be more than the deviation that you would observe from the silver meal heuristic, it says. Again, this study is performed over 20 test problems only, so we cannot make any generalization. But again, we should see at this point that silver meal heuristic and part period balancing heuristics are almost the most successful heuristics among all of these load sizing heuristics. Okay, so this is the end of module 6. But there is one final comment that I would like to make, and I'm just going to finish. Now, please be careful. I'm just going to come back the first example that I have mentioned. So we have a demand profile here. And we have said that the current on-hand inventory is 35 units. Now you see this 35 units is always meeting the demand of the first period, and we were not considering the first period at any solution that we have performed so far, right? Now, if this 35 units on-hand inventory was 30, then the first net requirement will be observed in the first period, right? Now, if you have a on-hand inventory, my friends, then it's a good idea to subtract this on-hand inventory from the first week's demand to adjust the first week's demand. So here's the thing. If on-hand inventory was 20, then I would subtract these 20 units from 35 and I would solve my problem as if I have 15 units of inventory, 15 units of demand in the first week and no on-hand inventory at all. So by subtracting the on-hand inventory from the first week's demand, I adjust it and I assume that I have no on-hand inventory and I have an adjusted demand. Okay. Now, at this point, you may ask, what if we have more than 35 units? Obviously, you are just going to ignore the first week and subtract the remaining amount of on-hand inventory from the second week, and you will start to solve your problem from the second week. So what happens instead of aiming to an ending inventory level of 0 units? If the inventory manager says that I want to have at least 10 more units as the ending inventory in the planning horizon, in the end of the planning horizon. So let's just say in this problem, we want to end up with 0 units of inventory in the end of the 10th week, but let's just say we want to end up with 10 units. In that case, you can adjust the demand of the last period from 55 to 65, my friends. And if, for example, if the manager wants to end up with 20 units, then 55 must be adjusted as 75. Okay, so a positive target inventory level in the end of the planning horizon can be included in the last period's demand. If there is a negative targeted inventory level, my friends, then this means, again, it will be added as a negative value. If, let's just say, the manager wants to end up with negative 10 units of inventory, then the adjusted demand in the 10th week will be equal to 45, my friends. Okay. Now, there is a very, very nice example related to this final concept that I have mentioned in the exercise set. I am leaving it to you to study, and this is the end of the 6th module. I hope to see you in the classroom in the next module. Okay, so thank you for watching.